Yeah, g'day, Mark here, and welcome back to my channel. Now this video is about well-balanced grinding wheels. I've already made 2 videos about my Balantron not working. So let's try and finish off the trilogy on a high note. Now the Jones Shipman 540 is one of the most common surface grinders. And they're common because they're good. Very intuitive to use with hydraulic traverse, so you don't have to wear yourself out by manually reversing the table the whole time. There's something about the design, even when they're heavily worn, you can still do accurate work with them. Now they only take pretty small wheels. I think 7.5 inches by 1/2 inch is the maximum size they're designed for, or 180 by 13. While surface grinders are only used to make parts that are accurate with nice surface finish, you would expect that you'd always want to have the most balanced wheel to give the best surface finish. However, I did get some feedback from some people who said with wheels this small, there's no need to balance them. But then I got feedback from others who said balancing's always good. And the finest way of balancing a wheel of all is, after doing this balancing with balance weights, is to use a Balantron. Now to balance a grinding wheel, you've pretty much got 2 options. Either you add mass to the light side, typically with balance weights like this, or you remove mass from the heavy side, like with a masonry drill, which is the brutal way of doing it. The Balantron gives the option of doing this in a much more controlled manner, which is a device that measures the vibration, finds the heavy spot, and then selectively wears off the part of the wheel in the heavy spot to bring it into perfect balance. Yeah, so Otto generously gave me this Balantron, which he picked up as bycatch with something else. It consists of an accelerometer to measure the amplitude of vibration, some analog electronics to do, I don't know, and a little diamond dressing thingy which bashes off the excess weight from the wheel. Now with my limited knowledge of electronics and especially troubleshooting, I wasn't going to get anywhere with fixing this thing. But luckily Peter in the UK offered to help me out, and just on the basis of a couple of photos of the circuit boards and inspecting and writing down the different component values of all the components I could see, he managed to reverse engineer the whole circuit, model it in some electrical modeling software, and create schematics. Yeah, that's real electro-magician territory. Unfortunately, he had to work with me to try and get the thing working, and I was the weak link in that chain by far. Now, I've been told a good place to start is to look at the power supply and make sure it's working. I've got our 240 volts coming in here. I've checked this fuse and it's fine. So from there, that AC power is coming into these 2 terminals, which is connected to the 240 volt or 110 volt AC switching. And from that switch, the selected voltage gets fed into the correct windings of this transformer. For my 240 volts, we should be using both of the primaries, and that should give us a 26 volt AC output. And that'll be on these 2 thick yellow wires, and those 2 wires terminate here. So let's probe and see if we've got 26 volt AC at that point. Okay, so we're slightly over our 26 volts, but that looks fine. Right, well, while I'm waiting for my next troubleshooting steps from Peter, I think I'll go ahead and continue cleaning up this box. Now, there are some people that say you shouldn't take off the patina of such an old toolbox, but to me, this one's not really patina, it's just gunge. So we'll clean it up a bit, and then I think I'll reseal the wood with some shellac. I was asked what I'm using for cleaning. It's just isopropyl alcohol. Most of the gunk came off just with normal cloth, and I'm just using a bit of steel wool to take off the hard stuck on bits. This is so cool, I think I'll even French polish it. It's a bit more work, but it generally gives a very, very pretty finish. So you start off just by rubbing shellac into the wood. Your French polishing pad, which has got like cotton wool inside it and on a cotton rag. Over time, you add more and more oil to the pad and less shellac and lots of elbow grease. The oil makes it glide over the surface while the lacquer fills up all the little defects and scratches and wood grain, and you end up with a very, very beautiful surface finish. I probably won't take this all the way to a complete sort of flawless finish because it really doesn't need it, but it still gives it a very pretty sort of depth and brings out the nice grain of the wood and stuff. Kind of feel like the Karate Kid, you know, wax on, wax off. So Peter had me check out the markings of these 4 diodes on the signal board, and I must say it's not that easy to read red diode lettering on see-through glass diodes. Okay, so I've got it set up now with the oscilloscope connected to the test point, which Peter found on the power card. So that system's on. You can see that the vibrations are quite high, because I've already had a play with it and found the position of maximum vibration. Now it seems to have found the peak vibration at about 50 Hertz. Is that because I've got a 2-pole motor turning 3000 RPM on a 50 Hertz power supply, and therefore maximum vibration should occur at exactly 50 Hertz? Or is it because I don't know how to set up an oscilloscope properly, and therefore what I'm really picking up here is just mains ripple? If I turn the motor off and it starts decelerating, that frequency should drop, which it is doing. Okay, and then until it loses signal. So this may well just be that the Austrian grid is incredibly stable at 50 Hertz. Right, so if I now turn on the actuator, there is some vibration in here. I've loosened it up enough now that if I pull it out, I can feel the vibration on it, and it vibrates back in. I'm really starting to think that the only problem this thing's got is mechanical, that it's just gummed up. Hey look, it seems like this thing does actually work electrically, it's just kind of gummed up, I think, so I can feel the vibrations in it now.
Okay, it looks a bit like a toothbrush for a big animal, like a horse or a bear or something.
A toothbrush for a bear, yeah, that'll work. Okay, since the input scopes out fine, let's switch this over to measure the output. Now the output to the 2 solenoids run via these 2 resistor capacitor pairs, and they're not symmetrical. This one's a 22 ohm resistor with 160 microfarads of capacitance, whereas that's a 15 ohm resistor with 250 microfarads of capacitance. So does that mean it pushes slightly harder in one direction than it retracts? I don't know. I took the opportunity to give this a bit more exercise, and it's now starting to move reasonably easy just with finger pressure. So that's good, it's getting better. So I've now got the oscilloscope set up to read the first of the solenoid output drives. So I think I've already got this tuned to maximum. Turn on the output driver. Oh. All right. Now feels like it's oscillating. So this is the output. Right, well I've now switched the sensor cable for the oscilloscope over to the other solenoid. Let's try that, switch on. That still looks kind of weird to me, that signal. Okay, I've reset the oscilloscope now for DC readout rather than AC. So let's try this again. Looking at one of my outputs, 50 volts DC. I'm not sure how to scale this. Is that with there? That's just a vertical move. I honestly don't know how to scale my output on this oscilloscope, and the manual's pretty difficult for me to understand. It's still not working. I've just switched over the scope onto the other output channel, so let's see what that looks like. The actuator's still getting more and more free, which is good, but in the retracted position it does nothing. If I pull it out, I can feel it vibrating in the middle, about here. And if I extend it, it vibrates and retracts itself. But let's be real, my lack of knowledge and competence of how to use an oscilloscope is kind of holding me back here. But luckily, Mike came to the rescue.
It's mail time. Well, not really. I've just returned from Vienna, where I picked up the insides of Mark's Balantron to have a look at. I've now got the Balantron slightly dismantled and set up on my bench. What I'm trying to do here is simulate the output of the accelerometer, which is in normal use mounted on the grinder whose wheel you're trying to balance. But because I don't have a suitable grinder to test with, and because it's more useful to me to be able to change the signal level and frequency, I've got a signal generator plugged in to the input of the Balantron here to simulate that. A signal generator set at 30 Hertz and 3 millivolts peak-to-peak output, and a scope looking at the input signal and the output of the Schmidt trigger part of the amplifier. This allows me to first of all check that the circuit is working up to that point, which it does appear to be, and also to look at how the Schmidt trigger output varies as I increase the signal level. Mark's friend Peter has done a great deal of work, I think, to reverse engineer a schematic for the Balantron. So I found it quite surprising that there's so little information that I've been able to find on the internet relating to the Balantron. I can't find a user manual. I don't think Mark has been able to either, or any other really useful information. So the work that Peter's done here is really invaluable in helping to debug this. And on the scope here, the yellow trace is the output of the phase inversion switch, and the pinkish purple trace is the output of the Schmidt trigger. What this is essentially doing is going to drive the actuator so that when the signal gets above a certain level in the positive phase of this yellow trace, the actuator is pushed out. So if the actuator is pressing in use, the actuator would be pressing against the grinding wheel during this section of the signal, thus removing a small amount of material as the heavy part of the wheel passes the tip of the actuator. So this tip is supposed to be able to move out and in as the wheel goes round, but in this particular actuator it seems very stiff, and so far we've not been able to actually see it working under power. As I change the amplitude on the signal, I hope you can see that the amplitude on the scope goes up and the purplish trace is consistently switching on and off at the same consistent levels as the amplitude changes, but that also means that the Mach space ratio, that is the duration the actuator is turned on for, decreases as the signal goes down, which in real life would mean that you're removing less material for each revolution of the wheel as the balance improves. As far as I can see, the circuit appears to be working correctly up to that point at least. So now I've added a third scope probe, the blue one here. This is looking at one of the drive signals to the actuator. The actuator is driven by two signals, one which pushes out, and then the inverse of that, which pulls it back in. So it does not appear to be a spring return sort of device, but it's actively pushed out and actively pushed back in again. And as you can see from the trace here, it's an inductive load, and then also there's an RC snubber network in series with this from the drive transistor, so it's quite a spiky signal, but the circuit is clearly trying to switch it, but nothing is happening. This switch here just disconnects the actuator so as not to overheat it through long use. I've just powered it off. Notice the meter jumps about a bit when you turn it on and off. That's just due to capacitors charging, etc., or discharging in this case. I think it's worth looking a bit more closely at this actuator, since the tip itself is very stiff. When I picked this up from Mark, you could just about pull it in and out with a pair of pliers, but it really didn't want to move by finger pressure. On the back, there are 3 2.5mm Allen screws. On the front, there appears to be some sort of seal or bellows, perhaps, and a circlip. Okay, so I've taken the back off the actuator here, and frankly there's not a lot to see. There are the 3 wires from the cable come through the strain relief, and there's a washer here. There's an O-ring seal, I hope you can see this, an O-ring seal here and another seal here, and these connectors. So it's quite nice, I guess, that it is connectorized for servicing. These 3 connectors do push through the hole in the middle. The end cover screws onto what I assume is a plate, which I'm guessing can be unscrewed. It has, apart from the screw holes, it has a pair of holes diametrically opposed from each other, which I imagine are for a pin spanner. I did try, not too hard, I have to admit, to unscrew this so I might be able to see something more inside it, but it was sufficiently tight that with the tools I was using, I couldn't move it. I really don't want to do any damage to it. So on the other end of the actuator, there is a circlip here, and I have to say that looking at this a bit more closely, I don't think this circlip is properly seated, as the 2 eyes of the clip are really close together. So I'm going to try and reseat that, put the cap back on, and see what happens. So I've put the back on the actuator now, and as I think you can see now, the circlip is properly seated, and in fact now I can easily push this in and out. It doesn't actually move very far, it's only 1 or 2 millimeters, but it does move quite freely. Whether that was because of the circlip or maybe just moving the cables inside, I really couldn't say, but that is quite a nice, easy movement. Okay, so as before, I have the signal generator, the scope hooked up just as it was in the last clip. I hope you can see the meter here. At the moment, the actuator is turned off. If I turn it on, lo and behold, it is battering backwards and forwards. But I'm just going to try changing the frequency on my signal generator here. So that's changing by decade. So this is 30 Hertz, 40 Hertz, 50 Hertz. You can clearly hear that the frequency of the actuator is changing as the input signal from the signal generator changes. Now there's one other thing which I have noticed. If I turn it on again, if I move this cable around here, it does stop. I think it's pretty likely that there's a break in the cable near the connector to the Balantron. So I think the final thing I'm going to do is to attempt to test this in a more real-world configuration. So I've plugged the accelerometer or vibration pickup device back in to the Balantron. Actuator is still connected. I'm going to use my embarrassingly out of balance bench grinder, but I've got this vibration pickup just sitting on my bench where it will pick up hopefully much less of the vibration than bench grinder is actually putting out, and just see what happens. Actuator on, and lo and behold, that probably doesn't show up on the video, but it is pulsing away, and you can probably hear that shaking bit. I really ought to either get some new wheels or a better grinder, but it served for a proof of principle, I think, here. So I would say that the Balantron is in fact now really working, as far as I can tell, as it should do, apart from probable broken wire near this connector.
Right, well, it's a good day today. It's a public holiday. I've got the day off work, and Mike's coming around with the fixed Balantron to try out. So I'm looking forward to that. Now, yesterday I mounted 3 grinding wheels and dressed them, and then the 2 bigger wheels both got a rough balancing. They're not perfect, but they're not too bad. The smaller wheel has no balance weights. Last time I mounted it, I gave it a rough balancing with a masonry drill, but it's been removed and remounted since then. Okay, so that's now the light spot. Now, before Mike brings back the actual guts of the Balantron, I guess I'd better put the handle back on this box. So let's just turn this on and let the spindle warm up.
Hi Mark, mail time.
All right, g'day Mike.
Special delivery from the UK.
Awesome, thanks very much. Oh, this is fantastic. You know, this morning I was re-watching my first Balantron video.
Yeah.
And I just realized what a complete random content video that is.
Hopefully this has arrived and packed.
It's done a bit of travel, huh?
Yeah. My wife brought it over. She came over before I did and put it in her checked baggage.
Oh, really? Well,
I wasn't sure whether I was going to check anything, but I did in the end.
well, big thank you to her for bringing it.
Oh, no worries.
We'll plug it in first and see if it's working.
Yeah, it's had a bit of a long trip.
It's everything plugged in, power on.
Yeah.
Okay, that's good.
I
Okay.
tweaked the meter so it sat back at 0.
Oh, thanks.
No, it's just that little screw at the front.
Okay, you'll have to put Mike's calibration sticker on it. Huh?
Yeah, right.
Cool.
Mike's non-calibration sticker.
Does the actuator do anything without vibration?
It'll do a bit if you tap the desk properly.
Oh, wow. All right.
What's that picking up?
It is true though. It's like
It's just random vibration.
if it's not on the the bench, it's picking something up.
Yeah.
Wow.
Interesting, there's not much on the meter there. But you do get a bit on the lower range.
That's pretty bizarre. What vibration it's picking up?
I don't
there?
know. I mean, it could be main sum.
Right. So at this point, we need to test this out and see if it's working.
Mm-hmm.
So the first thing we need to do is to wind the speed command about 20% over the target speed.
Yeah.
And since I'm on 50 hertz, target speed's 3000, I think, and 40 RPM according to the motor. So let's crank it up to about 3.6 or so. And the accelerometer I've been putting up here on this nice flat portion behind the grinding wheel. If anyone's curious, this is what the accelerometer for the fan shaft of, I think, a CFM 56 jet engine looks like. It's a 2-channel sensor, sending signals to each channel of the engine control. Right, so we can select our RPM range, which is currently correct.
So whereabouts should you hold it? About?
I think you're supposed to be in the vertical line, I'd say.
Okay.
Oh, yeah, turn it on.
And wrong one.
Oh, sorry, wrong one, yeah. I wouldn't push too hard. Okay, let's stop it and see what it's doing. It wasn't giving a nice clear signal.
It wasn't. No. doing something very weird.
Okay, so that first test was not a success because all it's done is abrade right around the wheel. Let's switch out to a known imbalanced wheel. The little wheel I've got's got the worst imbalance, so we'll switch that one in and give that a go.
It was actually vibrating properly, which it wasn't doing just now.
True. Didn't you say that there was sometimes issues with the cable? Could it be that the cable's not tight enough?
Maybe.
I mean, I've tightened that up now.
Okay. All right.
That was also part of the instructions, was trying both.
The orientation.
Where are we here? We're now a bit over 3,000. Now that's looking like a good signal. Oh, that's looking very good. No. So maybe we're just too well balanced before and I didn't know what to do.
Oh, well, maybe.
This is Mike and Mark, too well balanced. I'll go further out. There I was hitting that edge that I'd already put the divots in. Let me just go and turn the vacuum on.
Yeah.
And if it increases, then you 180 it, right?
Yeah. Going up.
So first, of course, connect it all up, put the sensor up, start off with your RPM 20% above your target RPMs. Use the 2.5 micron setting if you've got little vibration. Tune the thing until you reach your peak. Switch the vibration sensor between the two orientations to see which one's got the worst vibration. Make sure you've got your RPM here set to match what you've measured. The actuator on, hold it lightly against an unused part of the wheel. So the first thing I did wrong was I was trying to put it onto this area, but that's already been used, so I shouldn't have done that. If you've got more than 5 micron of vibration, do a static balancing with weights. If you've got an out of balance of less than 5 microns, then you can use the jackhammer to take bits off. Hold the jackhammer with 2 hands, lightly against the disc, and move it. So if you're under a 0.5 micron of vibration, take 2-second pauses and 0.5 second of touches. So once you get to the end, you want to do just nice little touches. If the vibrations increase, then hit the 180 button to switch over what it thinks is the high spot. Plus you can also move the point that you're touching through 90 degrees and see if that makes a difference.
And in these two figures, it's showing that with the sensor, we really had it like that.
We first measured with this orientation, then we switched to this orientation, and we found the higher vibration in orientation 2.
Right.
Okay, well let's try that again. Okay, well it definitely has taken off metal on only one portion of rotation. We thought this somewhere up here was the light spot. We initially took metal off close to the light spot. 180, moved that to the other side. Looking good.
I guess that's working.
Yeah, we dropped from 2.5 microns down to 0.5.
Yeah.
So let's try again on the pink wheel.
Okay. That seems to be working pretty well.
Yeah, it does.
According to the meter.
It also struck me that once we got down to about a 0.5 micron of vibration, that it stopped vibrating completely. It started.
What I would expect to happen with this is the electronics is triggering on the positive side part of the sine wave that the detector is seeing. And it's configured from memory in the circuit so that the actuator turns on, or comes out rather, at about 0.1 of a volt on the sine wave, and is turned off again when it comes down to about 0.5 of a volt. So what that will mean is that as the amplitude of the signal from the detector comes down, which will happen as the wheel gets more balanced, then the amount of time that the actuator is pushed out for should get smaller as a proportion of the overall sine wave. That's what I'd expect. I couldn't test that at home, so it'd be interesting to see if we can see any evidence on the wheel of that.
You didn't balance your bench grinder before returning it.
I thought that might be a bit destructive. It seemed to get to a minimum of about 1 and not want to go any lower than that, didn't it?
We didn't bother even dressing this, so
Yeah.
I was just thinking before, just imagine if you were selling this product today, what the user manual would look like in terms of disclaimers. Hold a handheld jackhammer next to a spinning fragile disc.
Yeah.
Okay, so it's definitely taken off away from,
Yep.
so the phase shift works. It's definitely taking
Yeah.
off material where it's supposed to. We've definitely got a change in vibrations. This is another one of those wheels which was given to me by my mate David. I've mounted it. I've not balanced it. We'll dress the outside of the wheel, grind a piece of steel and see what sort of surface finish we get. Then we'll balance it as accurately as we can with both balance weights and the Balantron. We'll redo half of the grind and see what the surface finish difference looks like. Other than it being an aluminium oxide wheel, I have no idea the grit or anything. It seems probably reasonably fine, but the markings are gone. Okay, well, it turned out that's actually a very fine grit wheel, and it was loading up very fast. My initial cuts were too heavy, and therefore it overheated the metal. I switched out to one of these open grit ceramic bonded wheels, just did roughing passes. That's now finished. I'll put our test piece back on, the out of balance fine grit wheel, dress it again, try and get it as nice as I can, and then we'll do the Balantroning. So I'll just dress this wheel again because I've loaded it up.
Yeah.
Well, for some reason, it didn't grind flat between the two different stones. We've still got a heavy roughing pass from the ceramic stone here. From the medium cuts with this stone, we got a little bit of overheating here, so I did a final dressing. But that's given us a very, very nice looking spot through here, which is going to be the bit we're comparing. Pretty darn nice surface finish. I'll just change the camera angle and see if I get a better view on it. We'll first do a balancing with the balance weights, and then we'll touch it off with the Balantron and get it as perfect as we can. And then do another grind across here, just a very light finishing grind, and try and stop sort of halfway across this bit. So this will be unbalanced, and this will be balanced. Right. Oh, that doesn't look very good.
Yeah.
Where's my chalk? Yeah, the way that dropped, it's definitely strongly out of balance. So I'll put a line there.
That's a lot better.
Oh wow.
Okay.
Boy, that was lucky. Nailed it. First time. It's going to buy a lotto ticket. Yeah, that is pretty well balanced, huh?
Yeah.
Which may well mean that it can't do anything better for us.
Yep.
Oh no. It'll try.
It will try, yeah.
Improved it.
Yeah.
Yeah, now it's starting to sound like a two-stroke.
Is.
Good as it gets?
Probably.
Oh, that was easy. While looking at it, the vibration rose a little, so we decided to do a little more. But then we just managed to make it worse. At the time, it was a confusing result. Here in the edit, I can see that we'd flipped the accelerometer on its side, so I should have been holding the actuator against the wheel at 3 o'clock or 9 o'clock, and not at 6 o'clock. Now, unfortunately, I had the magnet open to take the dressing diamond off, and I moved this part. And because I never ground the back side, there's no way that this is going back in the same place it was in before. So I'll just have to take some fine grinds, might have to redress the wheel again, try and get to this spot to a perfect finish. Well, what we can see here is it looks like the original grind with just the wheel loaded, it wasn't even balanced at that point, it was actually out of balance, is probably slightly better than the final one. Now, I think that's also because this is such a fine wheel that it loads up really quickly. With the Balantron, I'm not sure if we nailed the sweet spot. We might have gone too far with it.
We might have done, yeah.
So Mike, what have we learned?
I think we've learned that the Balantron does work. Maybe we're trying to achieve a level of perfection with the wheels beyond what we can, because it was quite well balanced to start with, according to the Balantron meter, and I'm not sure we actually improved on that.
Yeah.
With the final balance that we did. I guess another experiment one could do would be to deliberately unbalance a wheel.
Yep.
And try to make it better.
We had a pretty badly unbalanced wheel, this one, and the surface finish was not really
bad.
It was not bad.
No.
I do think that once you get down to that final couple of passes, the depth of cut of your second and third to last pass and the spark out pass probably makes more difference than the Balantron on this machine.
Yeah, and how much you're stepping over as well.
Yeah, true.
With each pass.
If you think of the world of grinding, like if we think of my friend Franz's TOS cylindrical grinder, which I think takes 400 millimeter wheels, which are 40 or 60 millimeters wide, the mass is like orders of magnitude higher than what I've got here. But it may well be that this is just not optimized for such small, light machines, and therefore we may not be gaining much by doing this. Let's try calling my mate and see if he's available this afternoon. Maybe we can pop out with the Balantron, give it a go on his big cylindrical grinder. We can help him with balance and see what the Balantron will do on a bigger, heavier wheel.
2 hours later.
To see whether the Balantron really works as well on a big wheel as it should, we've come out here to my mate Franz's place because he's got this big TOS cylindrical grinder. This wheel is 400 by 40, way more mass than the Jones Shipman. So what we're going to do first is just do a vibration survey on it and see what sort of readings we get. We've got the accelerometer up here on the spindle head. So first it needs to wiggle around a bit and fill the capacitors. What's the RPM? Spindle RPM 2000. So we're in that setting. Start there. Okay. Go for it. Okay, so now we've got the spindle running. We tune this until we hit a maximum. Okay. Tell me if you see anything move, huh?
Yeah, you've gone faster, I think.
Let's go to the high sensitivity. Down. Perfect. Down. There's definitely less scatter in the readings than we get with the Jones Shipman. A little more mass, I'd say. So that's the first orientation. Let's say 1.25. It shouldn't make any difference, should it? Because it should be the same frequencies, just different amplitudes. That's on the Jones Shipman. I always get a high reading on one and almost nothing on the other, whereas this is more realistic that you're getting vibration in both directions. This is the higher vibration. What you would do is, and just, if you want me to, okay,
Yes.
we'll go on to the, so I'll go around the back, I think, to do this. Yep.
Put down.
Introduce.
Yeah. Yeah, about 0.8. About 0.65.
So it's still improving. Franz is looking very skeptical of this whole process, right?
0.4.
Okay.
.25.
Wow.
.1. .5.
Now it's starting to make. Let's just stop there. Once you get down too close to no vibration, it seems like the signal starts like
Yes,
breaking
yes.
off the full wave, doesn't it?
And it worsens the whole thing.
Yep. So it's interesting. I did notice on this much coarser, much more massive wheel that I felt like I dug in a bit more than I did on the Jones Shipman. I can't turn the wheel because it's got a spindle brake, but you can see that most of the material removal is down in this area to balance it.
It doesn't have a spindle brake, it has a preloaded bearing.
Oh, wow, that's just the drag of the bearings?
12 Newton meters.
Oh, wow, so you can actually rotate it.
Yes.
Wow. It's definitely a more controllable process on the big wheel because data scatter is much wider on the Jones and Shipman.
Sure.
This was quite clear, wasn't it? It was
Yeah,
obvious improvement.
It was a pretty linear process, really, whereas on yours, there was a bit of randomness about it, really.
Who would have thought, Franz, that's one of my processes would have randomness, huh? Well, that's awesome.
But you have scratched my beautiful grinding wheel.
I have improved your beautiful grinding wheel.
The first grinding wheel of this machine. And when I bought it, only 12 millimeter of the first grinding wheel were missing.
This machine's done no work.
Yes.
We now know how to balance your
Yes.
balance
Perfect.
to things
Yeah.
to perfection, huh?
Yes. Yes.
Oh, it'll be interesting to see if you can notice an improvement in surface finish.
Yes. I watched your video last week. And this is what you need.
Yeah, these are these Norton dressing thingies for dressing diamond wheels, huh?
Yes.
So where I just used a spindle unbraked, you've got a bit of resistance for the dressing wheel. I was actually amazed that the way I did it, that it worked at all. These things have got a little flywheel brake on the back. They have just a little bronze brake shoe, a spring, and a screw. You know, the amazing thing about this is that Norton manages to sell these for, I think, €2,000. This is not exactly rocket science. Well, that's the brake drum. Sooner or later, this cap wears out, I guess, and then you make a new one on a lathe, because how difficult could it be?
Or you're allowed to buy a new one.
And the whole thing is just held in a very simple pillow block. This is the Norton number 2. I think this is the big one. I think they have a size number 1 as well, which is smaller. Because I was researching these last week after getting a whole bunch of comments that I need one of these. I would definitely like to thank Mike for fixing the Balantron. It's a bit embarrassing for me that it turned out to be a mechanical problem. So yeah, I should have been able to pick that up myself. Also, a big thank you to Peter for his support in the troubleshooting and making that that electronic model of the Balantron in software. That really helped.
Absolutely. I think that was really invaluable in helping to understand what the circuit was doing.
Of course, a big thank you to Otto for sending me the Balantron, which got the ball rolling on all of this. A big thank you to Franz for volunteering his TOS tool grinder for a checkout on this. And otherwise, thanks very much, Mike. And
It's an absolute pleasure.
yeah, stay in touch.
Will do.
And thanks to all of you for watching.